In this video, we're going to take a look at the organization of the elements, how the periodic table was developed. So in the early days of chemistry and alchemy, not a whole lot of elements had yet to been discovered. We only had a handful, like copper, gold, and silver, because you can mine those out of the ground and you find them in their elemental state. You can find copper, gold, and silver as they are. They're not in compounds. They can be, but not necessarily. And then by 1700, we had 13 known elements. So kind of recent time as far as man in history. The colony's already been developed. And we only have 13 elements in total. And then there are other ones they knew existed, but they weren't able to isolate them out of compounds. Like sodium, you never find sodium by itself, but sodium chloride is very common to be found both in soil and in the ocean. But the chemical process of electrolysis and getting sodium out of sodium chloride is very difficult and certainly not capable during their time. So scientists then had a plan to try and figure out how to find new elements. And they had a systematic approach now where they were trying to determine these new elements as opposed to just kind of helter-skelter all over the place, digging in the ground and trying to find new elements. Just like when you can't find your cell phone, it's a lot easier to find your cell phone retracing your steps and working through room by room, systematically trying to determine where your cell phone would most likely be lost and hidden, as opposed to just ripping apart every room of your house and turning it upside down and going all over the place and losing your mind and looking places multiple times, when in reality, if you just had taken a deep breath, slowly went through, it would have been a lot easier to find it. It may not seem all that impressive, but in a 10-year time period, we found 5 new elements. You can say, oh, only 5 elements, that's only one every 2 years. But again, relative to the fact it took thousands of years to get to 13, finding 5 in a decade was pretty impressive. But that now made a new problem. We didn't know how many elements there were to be found. How you know when you're at the end, and if you're just looking and there's nothing else to be found. So the way scientists kind of tried to help look for new elements and also figure out where they were in their finding of elements, they began to try and group these different elements based upon physical and chemical properties which they had. And then maybe by the number of elements in each group, you could determine how many were missing. So if we had groups of 5 and there are a couple of groups that only had 3, well, then you know those 2 groups probably have 2 other elements to be found. So the first real successful grouping was by J.W. Dauberreiner, and he put his elements into groups of 3, triads. And these triads were made up of, again, 3 elements with similar properties, usually with 2 that were similarish, and then a third one which would kind of connect them. So you think of like colors, like red and yellow, as we know as warm colors, are connected very well by orange. So red and yellow, yeah, the warm colors, and they kind of are similar, but when you add in orange, it really connects those 3, because orange is a little bit between red and yellow. And he would do the same with the elements. If he had 2 elements that were kind of related, and he could find a third one, which would make a nice group of 3, then that would work out really well. So like copper, silver, and gold, as we already kind of discussed, they make a great group of 3 because they have a lot of very similar properties, also hence why you find them in their elemental state. And so therefore they made a nice triad. So these triads were good, but not great, but no one really could come up with a better theory. So it stuck for about 5 decades until along comes Dmitry Mendeleev, a Russian chemist who pretty much adopted the actual periodic table as we know it today. There's also a German chemist, Lothar Meyer, who also was on the same exact path as far as getting to the periodic table, but Mendeleev beat him to the punch. And actually, in looking at increasing atomic masses and putting them in groups based upon these repeating properties, he actually then was able to take a step farther and use it to predict elements which had yet to be discovered. And then 6 years later, in 1875, we discovered gallium, and gallium had very similar properties to one of the holes in Mendeleev's periodic table, which he predicted the properties of density, melting point, and atomic mass, and they all were within real close precision of what that gallium element ended up being. So being able to predict those properties and showing how close his predictions could be, then scientists really started to believe he was onto something. And that something is called the periodic law, because then a few years later, along comes John Moseley, and we discover the atomic number and how every element has their own atomic number. And in Mendeleev's periodic table, we notice we have this increasing atomic number, and then as the elements are put in this chart by increasing atomic number, we see that we have this repetition of physical, chemical, and properties. Again, just like it sounds, periodic law, like period, a repeating pattern. So the Earth has a period of 24 hours in which it takes to make one full rotation. It also has a period of 365.25 days to make one revolution around the sun. And these elements, as you work across a period, then it comes back to the beginning, and that pattern repeats all over again. And so Mendeleev noticed this, and he decided, that's how he left holes in his periodic table, and also a couple weird spots like with tellurium and iodine where he flip-flopped them because tellurium actually has a greater atomic mass than iodine, but tellurium didn't fit in a family with fluorine, chlorine, and bromine, but iodine did. So he broke his own rule to make it fit the patterns of these properties. And that then set up these three very large groups of elements based upon similarish properties, these classes of elements, the metals, nonmetals, and metalloids. And the metals all are good conductors. They have a high luster, they're very shiny, they're malleable, you can bend them or whack them with a hammer and they don't break. And also ductile, you can draw them into long, thin wires. Conversely, nonmetals, they're poor conductors or insulators, they're dull, and they also are very brittle. They break when you try to manipulate them. And then metalloids are kind of in between. They have some properties of metals and some of nonmetals. So maybe it's a good conductor, but it's very brittle. Or it's very shiny, and it is a really good conductor, but again, I can't draw into a long, thin wire. So it has some properties of metals and some properties of nonmetals. And when arranged in the periodic table, we see them in these large groups together. The left side of the periodic table are the metals, the right side are the nonmetals. They're separated by a staircase you see below boron, silicon, and arsenic, and the metalloids are touching that staircase. So there's a lot more metals than there are nonmetals, and the metals have a very small range of properties that change between them as opposed to the nonmetals where you see gases and liquids and solids. The metals we see pretty much all the solids with the exception of mercury, which is a liquid at room temperature.